All right. Welcome to Technically Speaking. Excited to bring you this episode today on optimizing humidity control. A couple of things here before we get started. First, remember here for Technically Speaking, we do not use the chat feature. If you have any questions or anything that you want answered here as we go through, use the Q&A tool. You'll find that in the menu ribbon either at the top or the bottom of your screen. And at any point, go ahead and drop a question into the Q&A. You can either be related to what we're covering here today or really any subject related to property restoration. And at the end of the session, what we do is we go through kind of a town hall style Q&A period, and I'll do my best to answer absolutely any questions you've got related to the mitigation space. Also, if you have any thoughts on future content, I'd love to hear feedback on the content that we're covering here at Technically Speaking. So if you've got feedback there, I'll share my email address with you a bit later. You can also drop those into the Q&A as suggestions. So with all of that said, let's go ahead and roll in and get started. First, real briefly, if you're new to Technically Speaking, my name is Brandon Burton. I'm the Senior Principal of Industry Relations here at CoreLogic. I'm also the chair of the ANSI IICRC standards, the S500, the 520, S100, all of the various standards that are published by the IICRC. That's a process that I oversee for the IICRC as the standards chair. Very honored to fill that role. And a lot of what I bring in, Technically Speaking, I try to bring a lot of it from that stance and from that position and really focus on the industry's technical and really bring out some of what I like to call the industry's best kept technical secrets. And that's really going to be our focus today. We're really going to center on water mitigation and talk about the technical area of humidity control, often also phrased as dehumidification, et cetera. So with that in mind, let's go ahead and roll in. Keep that Q&A open and ready and at your fingertips. And again, any questions you've got as we go through, don't hesitate to drop those in, and we'll address all of those at the end. All right, so housekeeping out of the way. So humidity control is obviously a very important aspect of water damage mitigation, right? There are several facets to what is going to create a successful water mitigation project, and not the least of which being able to control humidity within a space, not only so that we can promote drying within that environment, but also so that we can prevent damages from occurring to otherwise unaffected materials, right? So I'm going to look at it kind of from both perspectives here a bit as we go into this. But where I want to start is just taking a really quick look at this flow chart that if you've been with me and Technically Speaking, this should look familiar. We've talked about this a little bit in a couple of the prior episodes where there are certain key processes that must occur every time in a water mitigation project. And this flow chart kind of outlines that. We're not going to go through the whole flow chart, but I do want to kind of identify the steps in this that are critical to humidity control specifically. So first and foremost, as we've talked about in the past, one of the first things we have to establish in any water mit project is we have to know precisely what is wet, right? Every project is unique, and part of what really defines the uniqueness of a project is how is that building constructed, what materials are present, how many layers are there in each of these assemblies, and how has the water migrated through those materials. And you've heard me stress a lot that when we think about this, we have to think about the projects in the context of materials, not assemblies, but a material, right? In other words, it's not a floor that's wet. It's, rebond cushion underneath a cut pile carpet, and that's installed over a plywood subfloor. The plywood subfloor is over a joist system that is insulated, and there's a crawl space beneath. That's the level of detail that we have to understand when we're defining what is wet, because that's going to directly impact all of our project variables, not the least of which being what we're going to talk about today, which is humidity control. Once we know what is wet, the next thing we have to talk about is what are we going to restore, right? So what will be restored and what will be replaced? And again, this is a critical question as it stands up humidity control, right? To keep this all in context of today's conversation. That decision, and we're not going to get into all the details of this today, but that decision boils down to three factors. What is the cost of the material versus its replacement if it's affected? Has the water caused any irreversible damage to the material? That would be the next thing I would consider in that restorability. And do we have issues with contamination, right? And I'll just abbreviate that because it's a long word. But those are the three factors that really stand up restorability. I could also argue into this some intrinsic and sentimental value associated with materials and replaceability and things like that. So we could spend a whole episode just kind of diving into those questions. But in order for me to understand how much humidity control is necessary, I've got to understand what I'm going to restore, right? What's going to be demoed and what's going to be removed. If we're not going to restore it, right? The answer being no, then we're going to go towards the demolition side. If we are going to restore it, then the next question in order to set up my project I have to define is how wet. And a lot of us overlook this, and as basic as this is, for the context of humidity control, it's critical, right? I need to understand how much water has actually been absorbed into these materials so that I can then understand what rate this moisture is likely to desorb, to evaporate, because that's really what's standing up my humidity control requirement, right? And again, we'll analyze this in great depth today. But from these questions, I can then start to gauge my equipment demands. And that's really where we're going to focus in today, is understanding how to size that up, how to evaluate that, how to understand whether or not we've been effective in that determination. And then ultimately, from that step forward, how do we evaluate the effectiveness, right? And that's the bottom half of this chart, this progress. If this all looks completely foreign to you, you've never seen me walk through this flow chart before, I'd highly encourage that you go to nextgearsolutions.com/webinars and take a look at the previous technically speaking sessions that we've done specifically on monitoring, where we dig into this flow chart very deeply. All right, so that kind of stands up where humidity control is going to be kind of brought into the process. So let's get into some of the factors related to humidity control. And I want to start with kind of, as Stephen Covey would say, start with the end in mind here and talk a little bit about just evaluating your humidity control once it's in, because I think that's an important place to start so that we can kind of back into the finer details of humidity control. So to start this off, first of all, when we're evaluating humidity control, two ways that we can look at humidity, right? We can look at relative humidity or we can look at a humidity ratio, sometimes referred to as an absolute humidity, specific humidity, all depending on how we're measuring it, what scale we're measuring it with. The most common scale that we use in this industry is something called GPP, for that specific humidity or humidity ratio, which is the more technically accurate term. And this stands for grains per pound. Now, I'm not going to get real deep into psychrometrics today. We've had a number of sessions where we've dived down that hole real deeply, or dove down that hole real deeply. So I'm not going to get real deep into that. What I do want to say for today, just to make sure that we're being technically accurate, is that although relative humidity is important and it's something that we do need to evaluate, in terms of humidity control, my assessments are going to be made in terms of grains per pound, all right, the humidity ratio, because that's the precise measurement of the actual amount of water in air. Grains is a unit of weight, and a pound of air is a given weight of air. So it's a ratio, weight of water to weight of air. Whereas relative humidity is kind of like the gauge on your automobile for your fuel, right? If I told you that my car parked in the parking lot next to me here, the fuel gauge says that I'm 50% full, that's like a relative humidity. You know that I'm half full, but you have no idea how much fuel is in the tank, right? Because you're missing things that it's relative to, right? Relative humidity. So for that reason, we don't use relative humidity to understand humidity control. We use the humidity ratio, or grains per pound. Now, when I make this assessment of my humidity for humidity control, just using some really generic examples, we're going to be at a certain amount of moisture in the air when we begin the drying process. Once we enact our humidity control and our air movement, generally what we're going to see is an elevation in that amount of moisture in the air. So, grains per pound, whatever these are, we could have gone from 10 to 100 or 80 to 70, doesn't matter. What's important for this discussion is that they are going to increase. We generally see this spike in humidity. However, humidity control means that once that spike has occurred, then over time, we're seeing this humidity begin to decrease within the environment, right? This indicates that we have humidity control. And that's literally what the phrase means, is that I have an amount of equipment installed in the environment that the humidity as a net is decreasing over time and not increasing over time. And that's the ultimate goal. That establishes that I have control. Now, as an industry, we do a really good job of taking this reading for humidity control once a day, right? And sometime 24 hours later, we take another reading and we establish where we are 24 hours later. The problem with that methodology of only taking this reading to evaluate humidity control every 24 hours is that it is inaccurate, right? Take a look at this dotted line right here. If I took those two readings 24 hours apart, then this would indicate to me that I do not have humidity control. And the reason for that is that, in that first, hour to 2 hours of the drying process, that's usually where this spike is going to occur, is right here in this 20 or this 2 hour range approximately. And that's where I begin to establish my humidity control is somewhere on the back end of that initial visit. So one of the first things that I want to encourage as a best practice is that when you're trying to understand whether or not you have established an appropriate humidity control, you need to take more than one atmospheric measurement on that initial visit, right? You take one when you get there, figure out where you're at, mark that down, write that information out. Install your drying system, let your dehumidifiers warm up, let your environment acclimate to what you've installed, which usually takes 15, 20 minutes at the most. And then once that is established and your dehumidifiers have gone into a full dehumidification cycle, then take one more reading approximately 20 minutes later, right? And all of that can be within the context of a 1 hour window. Within that 1 hour window, if you notice a decrease in your humidity within that 1 hour window, you have humidity control. However, if in that 1 hour window, humidity is continuing to increase, you are not done with that initial visit. You should never leave a project where humidity is continuing to increase without an indicator that it's beginning to decrease, right? And we're going to get that's really where we're going to spend the lion's share of our conversation today is around that particular problem. But you have to establish humidity control. All right. If you don't have humidity control, then that's where we run the risk of 24 hours later ending up with high relative humidities, which are what drive secondary damage. That's where we end up with slow drying over that initial 24-hour period. And that's kind of a catch-22 because if I don't have good humidity control for the first 24 hours of a drying project, not only do you run the risk of damages beginning to occur, but secondarily, you run into an even more significant problem, quite frankly, and that is that moisture, if it's really humid in that environment, your evaporation rates aren't maximized because the humidity is too high, and water is not just leaving the materials at that point; it's also absorbing deeper into those assemblies. The longer it takes you to get that bulk free water, that water that makes materials feel damp to the touch, the longer it takes you to rid the materials of that moisture, the wetter those assemblies are getting because you have absorption that is occurring into those materials simultaneously, right? Because water moves in every direction. So leaving that environment with a high humidity ends up creating a much wetter project, wetter materials that are going to take much longer to dry. So that's the other reason why this is so critical. We have to establish that humidity control and know that we are removing water at a rate great enough to reduce the humidity over time. So to kind of drive that through in an analogy, I want to kind of explore this example here of a bucket, right? Not the greatest drawing of a bucket in the world, I apologize, but that little rectangle in the middle of my screen, that is a bucket. And in this bucket, I want you to imagine that we have a flow rate of water that is entering the bucket and a flow rate of water that is leaving the bucket. And we have these little levers, these little valves that we can use to control that flow rate in and that flow rate out. Now, in this bucket, there is a certain amount of water that is already present, right? Let's say that's our water line right there. If the water line in this bucket is increasing over time, right? So this is going up, then obviously the water is flowing in at a greater rate than it is flowing out, right? So that would mean that more water is being added, less is being removed. The net impact is that we're seeing an increase over time. And again, the way to drive this home in the analogy, the way we would evaluate this is by looking at the grains per pound within that affected area, right? If grains per pound are increasing, then that means that water is being added to the air in that environment faster than it's being removed. So this is an important observation, but the reason I drive this really simple analogy isn't just to drive home the obviousness of what we just discussed in the previous slide. It's to start analyzing these levers. So this is something we fall short on in humidity control. The automatic assumption that most of us make when we see this happening and the humidity is increasing within the environment, the automatic assumption is that, well, I have one dehumidifier installed, that must not be enough. So let's add another dehumidifier. That's the automatic reaction. And most of the time, that's not the right answer. Okay. And I'm going to say that again because it's really important. Our automatic reaction is typically just add another dehumidifier. And most of the time, that is not the most appropriate action. To understand what I mean by that, we've got to analyze these levers. All right. So let's first talk about the lever that's letting water into the air, right? This rate at which water is being added to the air can be coming from a couple of different sources. The most obvious is that this is evaporation from wet materials, right? That's the most obvious. But ask yourself, well, why, if that's the problem, why is there more evaporation than my dehumidification is capable of handling, right? Especially if you use the example dehumidifier calculations that are in the S500, those are gauged to handle, the amount of evaporation that you should be expecting based on the size of the wet area that you've established, right? You measure out the area, you find out how much surface area we're dealing with. You assign a class of water to that. You run a calculation, cubic footage divided by a factor, et cetera. And that gives you an amount of dehumidification that should be adequate unless there are more wet materials that you didn't discover. So are there affected areas that you didn't discover? And is that the reason why the installed dehumidification wasn't adequate? Will adding a dehumidifier fix that? Well, no, it won't for several different reasons. Number one, if there's more wet material that you were not aware of, you're not monitoring that material. How will you know if it ever dried, right? You probably didn't extract that area. Is there bulk water? And evaporation is the wrong way to deal with bulk water, right? It should be properly extracted. Okay. So it could be this evaporation from wet material is because there are wet materials that we didn't discover. Another thing is there could be more than one source of water, right? Is there a source of moisture that was not identified? And this could be the case in more complex water damages. If the reason for this water damage event was because of frozen pipes and we found the break in a pipe, that's wonderful. But was there more than one, right? Is this because of area-wide weather events where we had wind-driven rain and we found where the water came into a building in one location, but was there more than one, right? And again, will adding a dehumidifier fix those problems? No, it's not going to fix those problems. The only thing that adding a dehumidifier does in that situation is mask the evidence of that problem. And again, that's really critical. So I want to say it a second time. Adding a dehumidifier when there is undiscovered water sources or undiscovered wet material only masks the issue, right? It's like taking aspirin for the headache. It doesn't cure it, right? It just covers the symptom. So it's really important when we discover this that you dive deeper and start asking yourself why. Don't just add a dehumidifier, ask yourself why. Another reason that we could be having this problem is because of infiltration. So infiltration means that we're getting moisture that is entering the structure from somewhere other than inside that space, right? So what is your local weather? What's the humidity like outside? Is the grains per pound outside higher than they are inside? If the humidity outside of the building in terms of grains per pound are higher than they are inside, then you are fighting some level of infiltrating moisture. It doesn't matter what the relative humidity is. It doesn't matter if it's raining outside. What matters is if the grains per pound are higher outside. If the grains per pound are lower outside, you are not infiltrating moisture. You're exfiltrating moisture. It's actually helping you. It's not hurting you, right? It has to be that the grains are higher outside. There has to be a higher quantity of moisture outside. That infiltration is adding a dehumidifier the right fix? Maybe, right? But maybe it's turning off the exhaust fans in the bathroom and in the kitchen. Maybe it's controlling the ingress and egress and occupancy so we're not ventilating so much of the outdoor and indoor air and mixing and commingling that. There could be other solutions that could be more practical or more efficient for managing that infiltration. Now, it may be that we just need to add additional dehumidification, but unless we ask that question why and identify that it is infiltration, we don't understand all the options that are available on the table, and we're not going to apply the most efficient option, right? So that's lever number one. Lever number 2 is the rate at which water is being removed, right? Now, the rate at which water is being removed is partially dependent upon, the capacity of the dehumidification that we have installed. It's partially dependent upon that, but it's not entirely and solely dependent upon that. For instance, you may have installed a 100 pint per day low grain refrigerant dehumidifier when your math said you needed 90 pints, right? And you're 10 pints over the minimum requirement, which is great. You have a nice, healthy amount of dehumidification. But if you were there on your initial setup and the hour meter said 0, and then you come back 24 hours later and the hour meter says 2 hours, adding another dehumidifier is not going to fix that problem, right? What's happening there is the dehumidifier is not running constantly, right? Property owner comes home, they don't like all the noise, they turn off the dehumidifier so they can get some sleep. They're not trying to hear all the drying equipment in the background. Maybe it's not property owner, maybe it's just property occupants, right? And when you get back to do your monitoring, miraculously the dehumidifier is running again. You take your readings, humidity is increasing in the environment. You think, I didn't install enough dehumidifiers, so you put in a second one. All you really did was give them another power button to hit when you leave, right? So again, if the issue there is that we're not getting constant operation from the equipment, then adding an additional piece isn't going to solve the problem, right? The problem is that the equipment is not in operation when we're not there. It could also be that the dehumidifier is not properly performing, right? And we would evaluate that by measuring grain depression, right? Evaluating the water coming into the dehumidifier versus the water leaving. I'm going to talk a little bit more about grain depression later. So if that term is brand new to you, don't worry about it. But generally speaking, if the water is entering at 80 grains per pound and leaving at 60 grains per pound, then I'm removing 20 grains of water per pound of air, right? And we'll do some math with that later and understand what that value really represents so you can turn that into something meaningful because even for me, and I've studied psychrometry for 30 years, talking in grains really makes it difficult to visualize whether or not that dehumidifier is operating properly. So anyway, it could be the performance of the dehumidifier. If I'm not getting good performance out of the dehumidifier, then adding a dehu isn't the right solution. Swapping the dehumidifier out is the right solution, right? So the reason I explore all of this is because it's important that we drive home that when we are evaluating your humidity control and we observe that the humidity control is not adequate, humidity is increasing over time, it's really important that you ask the question why and look at both levers, right? And that's the reason why I really wanted to stress this. We have to look at lever number 1. How much moisture is being added to the air? Is that different than I expected? What are the reasons why this could be more than I expected? And then once we're done with that analysis, then look at lever number 2. Why am I removing less water than I expected? All right. And is there a factor here that I didn't consider or something that I need to address other than just adding another dehumidifier? Now, at the end of the day, if adding additional dehumidification is what we're left with, then so be it. Adding additional dehumidification is what we're left with. So humidity control analysis, all right, and that's what this analogy is for us, and really understanding that humidity control is two sides. It's the rate at which humidity is being added to the air and the rate at which humidity is being removed from the air. Now, the next factor we need to drill into with humidity control deals with the other elements of establishing a drying environment. And then two big elements I want to talk about. I want to talk about managing drying chambers, and I want to talk about managing airflow, because both of these are very critical in properly establishing humidity control. I also want to make a note, if you wanted to go on to nextgearsolutions.com and look at some past, technically speaking, episodes that really drill into both of these. In season 3, episode 1, I get really deep into drying chambers and managing drying chambers. And also in season 3 and episode 4, I get real deep into the management of airflow. And I'm going to cover some of those principles here. But if this is really interesting conversation to you and something you want to learn a lot more about, please drill into either one of those episodes and get a full hour just on either one of those topics. But first, let's talk about chambers. When we're dealing with moisture in an environment and that moisture has affected, particular materials within my drying space, when we establish drying chambers, all right, when we want to establish humidity control, we first need to establish the chamber we're going to control the humidity in. And by chamber, what I mean is that we have to define kind of the outer limit of the affected area, right? So here I've drawn out that we have all of this affected within the space. This is my water migration. So all of this is affected within this particular structure. A drying chamber looks at the depth of that water penetration into those assemblies and into those materials. And what we have to do is we have to establish airflow, circulation, or communication between the air in and around all of the wet materials throughout that space. And that may require that we have one or more drying chambers. And to kind of drill that a little bit deeper, a single drying chamber may be adequate to deal with most of this wet area that I've just identified. But in this particular case, I know that we're going to need at least two. And let me explain the reason behind that and then relate that back to how important that is to humidity control. Uh, the reason I know I'm going to need at least two is because I have to circulate all of the air within a drying chamber so that my warm, dry air can get to everything that's wet, and the evaporating moisture can be moved away from those wet materials and can be managed through my humidity control system. Well, that would be a really bad idea between the air down here, where I have a bunch of wet surfaces in my crawl space, versus the air up here in my living space, right? These two air masses should not be exchanged with one another. There should not be circulation between the two. So I know at a minimum, just because of the cleanliness of air, I'm going to have to manage two entirely separate drying chambers. Now, the next question becomes, is this space and this space going to be in the same chamber or not? I've got two separate rooms here, and will these two separate rooms be inside of the same chamber? In most cases, the answer is going to be yes. If it is possible for me to move the air from one of these rooms and into the neighboring room and back again through circulation, then these should be the same chamber, right? A drying chamber is not a wet room. A drying chamber is a series of rooms and spaces through which you can manage the air through circulation. So these should, as long as there's a doorway or an opening between this kitchen and this living room or whatever this is, these should be managed at the same drying chamber. And that will be done through circulation of air, right? Through the proper placement of air movement. And this episode up here on airflow gets into a really in-depth discussion on how we do that with air movers and how we establish that circulation. The main principle is that to establish that I do have proper humidity control and a proper chamber established, I measure my psychrometric conditions in one room, my temperature and humidity to be exact, and I measure those conditions in the next room. And if I have appropriate circulation in my chamber, those will match. The temperature and humidity will be the same between those two spaces, no matter where my dehumidification has been installed, right? My dehumidifier could be installed in this room. And as long as I have appropriate airflow between these two spaces, then the temperatures and humidities are going to match. There's a reason why we use 1,000 and 2,000 cubic foot per minute air movers to move air between spaces within a structure. So we get many, many air changes per hour throughout that entire drying chamber. All right. So that would establish that I'm going to need just a single chamber for that upper space. But here's where we commonly, in humidity control, where we commonly overlook kind of our chamber setup, is what I've just drawn out for you addresses well the visible, accessible surfaces within this environment. What it does not address very well are the surfaces inside of this interstitial cavity, or the surfaces inside of this interstitial cavity, or if this is a hardwood floor, the surfaces beneath this hardwood floor. So as we establish this chamber and this air flow so that we can control humidity, you have to control humidity not just in the open visible space. You have to control humidity in each space where water is evaporating. If water is evaporating to the inside of that wall cavity, to the underside of that hardwood floor, to the from the wet insulation on the inside of an exterior wall cavity, anywhere that water is evaporating, where there are wet surfaces present, my humidity control needs to be established in that location also. And that is done again through air movement, right? Once I've installed the appropriate amount of dehumidification to remove that excess moisture and maintain my humidity, I have to use air movement as my transportation system to ensure that that warm, dry air is being delivered to all of those drying environments, right? So that drying chamber and all of those environments that are drying within it all need to receive that air movement and that airflow. So that's kind of my next principle in this, is that as we are managing our drying chambers, and again, I've got a great session on that back in episode 1 of season 3. It's really critical that our humidity control is being established throughout that entire environment where we have wet materials present. Okay. So let's go ahead and move on to kind of another example of this in using air movement to manage my humidity control throughout a space. But this time, instead of doing a cross section on a schematic, let's do kind of a top-down view on a schematic here. And kind of apply the same concept. So again, I'll establish a wet area here. Let's draw out an area of migration. Let's say that this is my area of migration and everything inside of this area is wet. All right, let's start talking a little bit about drying chambers. If I can establish air movement, let's say my dehumidifier is installed here, just to start the first part of this drying chamber conversation. And now let's establish some air movement. If I can communicate and circulate the air from this room into this room, and from this room into this space, and from this room into this space, and into this space, and into this space, then we can call all of this a single drying chamber, right? All of these are open to one another. There's a hallway that connects them. There are doorways that connect them. So this should be well established as a single drying chamber. The problem we run into is that we have this barrier, this common wall between what is likely two different apartment units or condominiums, and there's likely no opening, no entrance, and no ability to pass air through that wall into the neighboring space, unless there was damage that caused me to open that wall, right? So if the water source was inside that wall in the kitchen area, and we had damaged materials inside that wall, and we opened that wall, that common wall, then it would be potentially possible for me to then establish airflow and communication between these two spaces. Most cases, that's not going to be what we have. So we'll end up with drying chamber 1 as unit 1 and drying chamber 2 as unit 2. And then again, to validate that my humidity control is effective, and this is the key and something I really want to really drive home is hopefully a point of action for you, or an actionable item to deploy in the field, is take a temperature and humidity reading at one location in your chamber and at the opposite end of your chamber. You have humidity control if both of these readings are the same. And what I mean by same is very, very little difference. If you've established your air movement properly, regardless of how effective your dehumidification is, if you don't establish that air movement properly, you may have great humidity control in this area and really poor humidity control in this area, right? And again, just to drive home how important this is, if you dry 80% of a job beautifully in 3 or 4 or 5 days, but then 20% of that job takes 8, 9, 10, or 11 days, then the job took 11 days, right? It doesn't matter how well I dry the 80%, it's how well I dry 100% of the project. That's what defines preventing damage. That is what defines my customer satisfaction for how quickly, the irritation of drying is back out of their lives and they can have their home back or their business back or whatever else it is. And that, again, all comes down to appropriate humidity control. So humidity control is having equal control over that whole space, right? Not just over the area where my dehumidification is installed. All right. And again, I'm about halfway into the material here. As I hit this halfway point, I just want to remind everybody, if you could, make sure if you have any questions on any of the stuff that we're walking through here today, do not hesitate to hit the Q&A tool, open that up and start dropping some questions in there. I have not seen any questions drop into the Q&A yet, so I just want to drop that out as a reminder so that we have lots of to talk about here in our town hall session at the end. All right, so now let's transition kind of more into the equipment specifically and humidity control. The most common type of humidity control system that most restorers are using today is a dehumidifier, and more specifically, a refrigerant dehumidifier. And I want to talk a little bit about the inner workings of a refrigerant dehumidifier for a moment, because if you understand the inner workings of a refrigerant dehumidifier, you can leverage more humidity control out of it by really mastering that machine and understanding what it's doing and what its limitations are. You can more effectively use it for humidity control, and you can more effectively evaluate its ability to and how well it's performing, I should say, against what you would expect from that particular piece of equipment. So first, basics, refrigeration basics. And you're not going to walk out of here being refrigeration certified, but you'll be pretty close. So inside of a refrigerant dehumidifier, there are four parts or four pieces inside of that machine. One of those pieces is a compressor or a heat pump. And this is the motor that is doing the work inside of your refrigeration system, whether it's a refrigerator or an air conditioner, dehumidifier, doesn't really matter. They all have the same basic parts. And what this little device is doing is it's pumping refrigerant through this system, right? These chlorofluorocarbons that are so wonderful for our environment, right? That's what that little device is doing at the bottom. Now, the refrigerant inside of this system is being pressed into one coil that looks a lot like the radiator in a car, right? It's a bunch of fin tube coil design. It's then being transferred over to a second coil through a restriction device, right? That's restricting that flow into a second coil that looks a lot like the first one. And then it returns back to this little heat pump. And this refrigerant just keeps cycling through this over and over and over again. What makes the magic in a refrigeration system is that on the first side right here, on side number one, we are compressing a bunch of this gas. We're concentrating that refrigerant gas. This restriction device in the middle in coil number two is creating the opposite effect on the backside. We're expanding the gas. Okay. And the magic in this is that when you take like the air in front of you right now, that if you were to kind of hold your hands out and kind of imagine air about the size of a basketball between your hands, that air has a certain temperature, probably 70 degrees Fahrenheit approximately. If you were to take that air in your hands and squeeze and compress that air down to the size of a softball, right? So if you were able to compress that air down to the size of a softball, what you'd be doing is taking the heat that is in that air and you'd be concentrating it into a smaller airspace. And the net effect is that the temperature would be much higher because now the same energy is in a smaller space. And that's what happens on the first coil right here. Through compression, we're taking the amount of energy and making a much higher temperature. On the other side, we do the opposite. So imagine your hands out in front of you. You've got air the size of a basketball. Now expand your hands and expand that air to the size of a beach ball, right? Now you're taking the same heat and diluting it over a greater space. And what ends up happening is you end up with a high temperature on one side and a low temperature on the other side. Now take the air from your drying environment and run that air straight across both of these coils. You have air that is warm and humid, and you run that warm, humid air across the first coil. That first coil, its job is to remove energy because it's cold, right? So it's going to draw energy out of that air. And as it does so, remove energy from the moisture in that air and cause it to condense. The same thing that happens when you take a cold soda can and you put it on your counter on a hot, humid August day. And that soda can is absorbing the energy out of the air and causing the moisture in the air to sweat onto the surface, right? And that's in essence what's happening on that first coil. On the second coil, we're putting the heat back into the air and then venting that into the room, and you end up with warm, dry air. Now, here's the magic that I want you to walk away with in understanding this. And this is the key to one of these kind of drying Godzilla tips of really understanding the performance of your refrigerant dehumidifiers. Okay. And it's going to require, a little bit of an understanding of psychrometrics. And again, I'm not going to dig real deep into that aspect, but if you walk away with the basics of this, you're going to understand much better how to evaluate the performance of your dehumidifiers. Okay. So on the first coil, what's happening is we're taking the temperature of that air and we're cooling that air down to what we call its dew point. Okay. And dew point is basically how much energy is required in air to support the amount of moisture in it, right? So if I got air that's 70 degrees and it has a dew point of 50, that means that if I cool that air down to below 50 degrees, it can no longer support the moisture it has. That excess moisture is going to literally sweat out onto that surface. And the more I drop below dew point, the more sweating I'm going to get on that surface, right? As that moisture sweats onto this surface and that moisture collects on this coil, what's happening is the refrigerant dehumidifier is absorbing the energy not from the sensible temperature anymore. It's taking the energy from the moisture. And all of that energy from the moisture that's condensing on the coil gets pumped over here to the second side and gets compressed as sensible heat. And then leaving the dehumidifier on the backside, all of that sensible heat is measured as a temperature rise. So here's the moral of the story. If air enters this dehumidifier at 70 degrees and it leaves this dehumidifier at 90 degrees, where did all that heat come from? Right? Where did all that extra temperature come from? It came from the moisture that collected on this coil system. The greater the temperature rise across your dehumidifier, the more water is being collected by that dehumidifier in operation. Kind of an aha experience if you think about it for just a moment. In most dehumidifiers, this compressor down here is also adding a little bit of that heat, like 5, 6 degrees, maybe 7 degrees at most. But if you look at your dehumidifier and you have more than an 8 or 9 degree temperature rise, the dehumidifier is working. If it's working well, you're going to have a 15 to 20 degree temperature rise. All right. So this is a really easy way for you to analyze when you're looking at your humidity control and saying, okay, I've got way more moisture in the air than I expected. Humidity is increasing over time. Why is my humidity increasing over time? Then you go to your dehumidifier and you measure that dehumidifier to find out if it's working. And what you typically do to measure that dehumidifier to see if it's working is you look at this thing called grain depression, right? And that's where we're going to go next here in a second. That's one way of understanding if the dehumidifier is performing. But a far simpler way to understand performance is this temperature rise. If you're getting a 15 to 20 degree temperature rise, that indicates that you are condensing a significant amount of water onto that dehumidifier's coil system, and that dehumidifier is performing well. There isn't necessarily a fault with the dehumidifier. Now, did you install too few? We went through that analysis earlier on in the conversation. That's a potential. But the dehumidifier's performance overall, the way it's working, the way it's operating, the health of that system is good, right? So at least it gives us that information so that we can rule out whether or not that dehumidifier is operating properly. All right. So now next, let's take a look at the other way that we commonly measure the performance on these dehumidifiers for humidity control. The other way that we measure these is through something called grain depression, right? And grain depression is a measurement of the humidity of the air entering the dehumidifier versus the humidity leaving. For example, if the air entering the dehumidifier is 80 degrees Fahrenheit at 60% relative humidity, right? Then we can take a look at that measurement and we can say, okay, how much moisture is actually entering the dehumidifier? Now, remember, when we look at humidity control, we don't use relative humidity. We have to pull out a psychrometric chart or our psychrometric calculator if we have one of those apps for our phone, and we'd have to convert this into grains per pound. That just happens to be about 91 grains per pound. And that's the unit of measure that we will use to understand how well the dehumidifier is operating. Now, this measurement by itself doesn't tell me anything. This is the air entering the dehumidifier. The next measurement I need is what's leaving the dehumidifier, right? That'll help me understand what the dehumidifier is doing. So I do the same thing, measure the temperature, measure the relative humidity, convert that into grains per pound. And let's say that the grains per pound leaving the dehumidifier is 70 grains per pound. In real basic terms, this means that the grain depression is 19. 21. If I could do math in my head, that would be nice. 91 in, 70 out. 91 minus 70 is 21. So I have a 21 grain depression. Now, what does that mean, right? Is that a good performing dehumidifier? Is that a bad performing dehumidifier? That number in and of itself doesn't really say a whole lot to us, right? Now, to understand what that number actually is, I'll give you the technical definition, right? Which I don't expect to to give you a whole lot of understanding, but I want to share it with you. That means I'm removing 21 7/1000ths of a pound of water for every pound of air processed by the dehumidifier. Does that tell you anything? It doesn't tell me anything. I know exactly what it means, right? Grains are just a unit of weight. A grain is a 7/1000th of a pound. It's just a scale for measuring how much things weigh. It actually comes from way back in the days of metric measurement and comparing things to the measurement of actually imperial measurement, and the measurement of comparing things to other things comes from kernels of wheat of all things. So it doesn't really tell me a whole lot. But there is a way to convert this into something that does tell me a lot. If you take your grain depression and multiply that by the CFM, and CFM is cubic feet per minute of air going through the dehumidifier, and then divide that by 71, it'll convert the grains of depression into pints of water removal per day. So grain depression times the CFM of the dehumidifier divided by 71. So I'm going to go ahead and do that real quick on my calculator. And we're just going to take this dehumidifier and we'll say, this dehumidifier, again, the grain depression was 21. And let's say the CFM on this dehumidifier is 300. So I'll multiply by 300, then divide by 71. And what I come up with is 88 pints. So this dehumidifier with a 21 grain depression is removing 88 pints of water per day. All right. That's a really good water removal rate if the dehumidifier is rated at 70, 80, or 90 pints, right? Then that's a really good water removal rate. Now, notice how that means a lot more to me than a 21 grain depression, right? It means a lot more to me than that grain depression. And again, that shortcut to get that math done is grain depression times the CFM of the dehumidifier divided by 71. And if you want to understand the roots of that math, what it comes from is that a pound of dry air is about 14 cubic feet in size. So if you take the cubic feet per minute of the dehumidifier, divide by 14, you get pounds of air per minute. You can multiply that by 60 because there's 60 minutes in an hour. You can multiply by 24 because there's 24 hours in a day. So you can do all of these steps to convert this into the actual water. This is just a shortcut. So it consolidates all of that down to just a couple of quick steps. So I'll say it one last time, mark it down somewhere, try it out and use it. Grain depression times CFM divided by 71. And the beauty of this math is that this math for humidity control and understanding the actual amount of humidity control from a system, it isn't just unique to a dehumidifier, right? If I go back to this analogy from this floor plan that we had earlier, let me go ahead and clear this ink out of here real quick. And let's say that outside we have taken a temperature and humidity measurement and we find out that outside there are 50 grains per pound. And in our drying environment, there are 90 grains per pound. And I decide, you know what, let's use some of that outdoor air to benefit our drying system. I'm going to go in the kitchen in here. And in the kitchen, I'm going to turn on this kitchen exhaust fan that is going to vent air out of the building at 100 CFM. And by dumping this 90 GPP air out at 100 CFM, that means we're going to draw this air in at 100 CFM, right? So now I'm going to get a grain depression between these two of 40 times a CFM of 100 and divide that by 71. So just by turning on the kitchen exhaust fan, I can do 40 times 100 divided by 71. I can get 56 pints of dehumidification just by turning on the kitchen exhaust fan. That's like adding another small dehumidifier, right? Now do the same thing in the bathroom for another 100 CFM. That's another 56 pints of dehumidification, right? So humidity control, in other words, doesn't just have to be about adding dehumidification. Humidity control can be any manner at which we are controlling the humidity in that space. And the beauty of this math is that it can help us understand the value of the other options that we have available to us on the table, right? So that's refrigerant dehumidification, the way that refrigerant dehumidification operates internally. That's understanding its performance. I did see some questions come in on that dehumidifier performance, and I'll get to those right at the end of the session here. So thank you for that, John, and others who have posted those questions. And we'll jump into that, into the town hall here at the end. I do want to talk a little bit also about other methods of dehumidification. In addition to refrigerant dehumidification, another methodology in dehumidification is something called a desiccant. Because of where we are on time, I'm not going to drive real deep into desiccants, but I do want to share with you that if you do have desiccant dehumidifiers, and that's something that you are using occasionally within your fleet, and you want a much better understanding of how they operate, how to leverage the benefits of a desiccant dehumidifier appropriately, and what projects to leverage that on. There's a really good episode we did on that back in season 2. So you can take a look at that, season 2, episode 7, where I dig pretty deeply into the world of desiccant dehumidifiers and how to really leverage the technology benefits that a desiccant can provide on the right projects, particularly in cold weather climates. when dealing with class 4 and specialty drying situations, and how to really leverage that low vapor pressure that you get from desiccants. So just as a kind of a tip there, if you want to get into the world of desiccant dehumidification and get that desiccant off the racks that's collecting dust because you're not using it, take a look at season 2, episode 7. All right. Because we're coming up on time here, I'm going to go ahead and press forward so we have lots of time for Q&A. As we round out the technical presentation piece and get ready for the Q&A, a couple quick things on the backside of this. Just so you know what's coming up here in Technically Speaking here for the balance of the year. We are still planning on bringing some content for you on the fire restoration side. Give you a little bit of an update to the reason why I haven't brought a fire restoration presentation into Technically Speaking yet. We're waiting for the fire standards to kind of finish out their publication cycle. There are 2 brand new fire standards that are in process. One is the S700, which is the structure restoration fire standard from a structural fire. The other is the S760, which is the wildfire restoration standard. Both of them have gone through their public review cycle, through the ANSI process, and both are very, very close to publication. There's some steps at the end that have to be completed to kind of dot some I's and cross some T's. And as soon as I know that we have an official publication date on those and all of those formalities have been complete, you'll likely hear me talk a lot more about it here on Technically Speaking. But what I plan to do as soon as those do publish is to go ahead and host some specialized topics in Technically Speaking directly on fire restoration, talk a little bit about those new standards, and hopefully have some of the members of those consensus bodies that worked on those standards come in as guest presenters for us here at Technically Speaking. So if fire is something that your business does and you want to learn some more about it and the all new standards that are coming up, watch for that on the Technically Speaking schedule. The other one they haven't quite got on the schedule yet that is still coming is also the S590 HVAC standard. This is a new standard that published late last year from the ICRC's ANSI standard library. And I'm working on getting a guest presenter in that chaired that particular standard so we can talk a little bit just about properly handling HVAC systems during a water damage. And as a restorer, when I encounter a centralized, heating and air conditioning system that has been impacted, how do we best manage that? If it's not impacted, can I use it? Should I use it for humidity control purposes and stabilization, et cetera, et cetera, et cetera? So we'll hear from the experts on that when we bring that episode. And of course, I got lots more from water damage I plan to bring you. If you've got thoughts on Technically Speaking content, my email address is brburton@corelogic.com. Feel free to email me often, email me frequently, anything that you would like to see in Technically Speaking lineup. And then last but not least on this slide, nextgearsolutions.com/webinars. That's where we house all of the recorded episodes of Technically Speaking. We've got like 30 some odd episodes that have been uploaded onto the website. So feel free to peruse those. All of those are there and available. Can make some really good content to drive your water cooler meetings on a Monday with your technical staff. What I've noticed some folks are doing with these episodes is they're actually assigning somebody to go through, listen to the episode, extract 3 or 4 learning objectives out of it, and then instead of watching the Technically Speaking episode with the rest of the staff, you have your technician deliver that content to your staff. There's no better way to learn something than to teach it, right? Highly encourage that type of practice, because if you have somebody in your staff that's taking the information and kind of translating that into their own words and delivering that to the rest of your technical staff, they will become the expert in that topic pretty quickly. That really drives the confidence behind the material. And with that, thank you for joining us again here for Technically Speaking, and we will see you again next month. Until then, take care and happy drying.